So the first lesson is on one-dimensional kinematics. So to clarify some terms here, first of all, we have dynamics, which is a branch of physics that studies how forces applied on objects affect the way they move. So examples are gravity, friction, and Newton's laws. But a sub-branch of that is called kinematics, and this describes just the motion of objects. Okay, so kinematics is only the like how something moves, but we're not talking about forces yet. And then one-dimensional means we're only going to focus on motion occurring along a straight line. Okay, so eventually we're going to have to do two, maybe even three dimensions with objects turning and going different directions, but for now we'll stick to one dimension. So objects are just going forward and backward along a single line. All right. So this slide gives some examples of one-dimensional motion. So driving on Highway 401, cars either go eastbound or westbound. Okay, so it's really just along a straight highway, or pretty straight at least. There's drop zone at Canada's Wonderland. The riders can only go up or down. So again, it's just along a straight line. So that's what's meant by one-dimensional, if it's going along a straight line. But then if you look at something like a race, so here's a map for the Toronto Marathon. You can see that there's lots of turns involved. They run through the city of Toronto for the marathon. So you might think, oh, well, that's two dimensions because they go left and right, but also north and south. However, you can actually consider races to be one-dimensional as well, because you really only follow one path. Like, there's only one path forward to go in a race. And you're either going forward or you're going backward on the course. Hopefully you're not going backwards, but yeah, you're only following one route. And we're going to call that direction forwards. So that can also be considered one-dimensional motion. Okay, scalar versus a vector. So this is from grade 11. Scalars are quantities that have a magnitude only. They do not have a direction. Any symbol for a scalar will not have an arrow or a harpoon on top of it. And some examples of scalars are distance, speed, and time. So distance, I'll often use the letter D. Speed, I'll often use the letter V. And time, I'll often use the letter T. Those are scalars. Vectors, by contrast, have both a magnitude and a direction. Their symbols have an arrow on top or a harpoon. I actually like to call it a harpoon. So some vectors you may have known from last year are displacement, which has this symbol, velocity, which has this symbol, and acceleration, which has this symbol. So all three of those symbols, I drew kind of a half arrow on top of it. I like to call that a harpoon, which is basically like a spear like a spear. It's got a hook on the end of it. Okay, so that's scalars versus vectors. So sometimes you want to talk about a vector, but only its magnitude, and you want to ignore the direction. Okay, so if you want to talk about a vector but ignore its direction, then you put vertical bars around it. You might recognize them as absolute value bars from math class. So this is what I'm talking about. You put vertical bars around any vector quantity, and that indicates to the reader that you're only going to talk about its magnitude, no direction. Okay, distance versus displacement. So two very important terms from last year. The definitions are written as the first bullet point here. So distance is a length of the path traveled. Displacement is a change or difference in position. It's the length and direction of the straight line drawn from the starting to the ending position. So They're similar in terms that they're both measured in quantities such as meters or kilometers or feet and whatnot. And they both kind of talk about how far an object travels, but they're also very different. Distance is specifically the length of the entire path. So it's like if you keep track of how many steps you take, that's similar, like you would measure distance the same way, except you do it in meters and not in steps. But displacement is different. Displacement, you only care about where you ended up compared to where you started. So in a whole entire 24-hour day, your displacement is actually often zero because you will often wake up and you might walk around all day long, but eventually you come back to bed and you're in bed until you wake up the next morning. So it's like you started at your bed and then at the end of the day you end at your bed. Your displacement ends up being zero. It's where you ended up compared to where you started. Whereas your distance could be many thousands of meters if you took many thousands of steps. All right, so let's do the example at the bottom. An object moves 12 meters to the right, followed by 4 meters to the left. Now, what is the distance? What is the displacement? So the distance, which I'm going to use the symbols that I wrote up in the notes. So the symbol is d for distance, and it's the length of the total path, or entire path. So the entire path includes the first 12 meters plus the next 4 meters. So that in total equals 16 meters. And that's the distance. That would get you full marks if you did that. How about the displacement? Part B. So the displacement, so the symbol, if you look at what's written in the notes, is delta D with the harpoon. It's a straight line from start to end. So it's the length and direction of, I'm going to say the red line. I'm going to draw it in red in the diagram here. So from the start to the end, looks like that. That red line is the displacement. I will label it with the symbol there. Okay, so the displacement is shorter than the distance, actually. It's actually 12 minus 4 meters. So that gives you 8 meters. And this would not get you full marks yet. Displacement is an example of a vector, so you also need a direction. So the direction would be to the right. And we write directions in rectangular brackets here. Okay, so that would be full marks. If you forget direction, you would lose half a mark. Okay. Next, we're going to talk about time. So time has a symbol of t. It's usually measured in seconds, but sometimes it's minutes or hours. You might have to convert in some problems, but the standard units are seconds. It's a scalar quantity. There's no direction associated with time. So therefore, its symbol does not have a harpoon on it. If I just use t, it refers to a specific moment in time. Another way to describe that is with the word instantaneous. So t is an instantaneous time. Whereas, I'm going to go all the way to the right here, delta t is an elapsed time. So all the way to the right here, elapsed time. It represents how much time passed during an interval. Okay, so It's like how much time a stopwatch would say if you timed how long something took. Okay, so delta t is how long something takes, but t by itself is just one specific moment. They are different things. And then I will often communicate intervals of time with the notation expressed in the middle. So I'll circle it. This notation here, if you were to translate the mathematics symbol for symbol, it would say A is less than T is less than B, but that is not easy to like think about in conversation. So I like to just say the time between A and B. Okay, the time between A and B. That's an easier way to say it. All right, so let's look at the example down below. A speeding vehicle passes a police cruiser at t equals 0 seconds. At t equals 5 seconds, the cruiser begins chasing the vehicle. The cruiser catches the vehicle at t equals 30 seconds. A, what is going on at t equals 3 seconds? So they're asking about instantaneously at the 3 second mark, what is happening? So I would say that the speeding vehicle is driving, but the police cruiser is still at rest. Okay, the police cruiser does not begin chasing the vehicle until the 5 second mark. So at the 3 second mark, it's still at rest. So the speeder is driving, cruiser is at rest. B, identify the time interval that the cruiser was chasing the vehicle. So time interval, they're referring to the middle column of notes there. They want me to express between what time and what other time was the cruiser chasing the vehicle. So that would be between 5 and 30 seconds. If you read the question carefully again, the cruiser is chasing the vehicle between 5 and 30 seconds. But instead of writing that out as a whole sentence, I want you to get used to this new notation. So I would write it as follows. 5 is less than t is less than 30. And I'll put the units down at the end there, seconds. Okay, so that's the mathematical way to say the time interval between 5 and 30 seconds. C, how much time elapsed between the speeder passing the cruiser and the cruiser starting the chase? So that would be 5 seconds. Okay, 5 seconds elapsed between when the speeder passed the cruiser and when the cruiser started chasing it. But the goal for this slide is to get you to use the symbols properly. So instead of just writing 5 seconds as your answer, I'm expecting to see delta t equals 5 seconds. Elapsed time is a delta t symbol. And then D, how long did the cruiser drive before catching the vehicle? So the cruiser drove, well, it would be how much time from between 5 and 30 seconds? Well, that would be 25 seconds. But which symbol do I use to communicate this answer? How long did the cruiser drive for? Well, I would consider that an elapsed time, okay? An elapsed time. And that elapsed time can be calculated with subtraction, 30 minus 5, and that equals to 25 seconds. Okay, so this was a really symbolic slide based on time. Average speed versus average velocity. So now we're talking about how fast objects are going. Now there's two different measures of that. One is speed and one is velocity. And these are best defined as formulas, actually. So average speed is defined mathematically as distance divided by elapsed time. And average velocity is mathematically defined as displacement divided by elapsed time. Okay, so that makes speed a scalar, and it makes velocity a vector. That's why there's a harpoon for the symbol for velocity. There's lots of possible units for speed and velocity. The standard ones are meters per second, but if you're driving cars, you often talk about kilometers per hour. Sometimes you might talk about meters per minute for whatever reason. Kilometers per minute is, or minutes per kilometer even, is something runners use to talk about their pace. All right, so we're gonna practice using these two formulas for average speed and average displacement. So the letter is V for both of them. For speed and velocity, it's V. But velocity, since it's a vector, has a harpoon over it. And we use the subscripts AV to stand for average, because it's hard to stay at the exact same speed the whole time. You're driving down the road. Sometimes you're slower, sometimes you're faster. So it's usually we just talk about the average. All right, example. Rayshawn runs a there and back in the gym, which means he sprints from one end line to the opposite end line and then back to the first end line. The distance from end line to end line is 28.2 meters. Rayshawn takes 6.3 seconds to complete the there and back. What is his average speed? I'm going to draw a diagram first, actually. So we have the gym, and this can be the one end line he starts at. And this can be the opposite end line. And the there and back looks like this. He runs, sprints to the other end line, touches the line, turns around, and sprints back. Each direction has a distance of 28.2 meters. Okay, so average speed, if I go just directly with the formula written there in blue, V average, V subscript AV equals distance over elapsed time. So the distance is the length of the total path. So that would be 28.2 times 2, because you got to go there and back. And then divided by the elapsed time, which is 6.3 seconds. Okay, so I will throw that into the calculator here. And it gives me an answer of 8.95. However, I do need to round this to two significant digits because of the 6.3. So that would actually end up rounding to 9.0. And the units of speed in this case would be meters per second. Okay, the average velocity. I'm just going to go straight with the formula in purple there. That is the displacement divided by the elapsed time. Now the displacement is 0. The displacement is 0 because the ending position is at the same as the starting position. So 0 divided by the time of 6.3 equals 0. All right, so that is the average velocity. Now, the direction does not matter when the answer is 0. Okay, there's no direction when the answer is 0. Okay, so this would get you full marks. Now, what would not get you full marks? Well, if you, let's say, forgot to write the harpoon during part B, you would lose marks. If you wrote harpoons in part A, you'd also lose marks. And it's also, if you did not round to significant digits for part A, you would also lose marks. So, let's say you wrote an extra digit. So that would be 8.95 actually. You would lose half a mark. Only the super careful students will never lose significant digit marks or vector harpoon marks. And hopefully you just get better at it as the semester goes on to remember those little details. Okay, now the previous slide was about average speed and velocity, but then we can talk about instantaneous speed or instantaneous velocity. So theoretically, instantaneous speed is supposed to tell you how fast an object is going at a specific instant. For example, what a car speedometer will show in the car, or what a radar gun will show if an officer is trying to catch speeders. It's supposed to show the instantaneously how fast a car is going. So in the diagram on the left there, it's showing an instantaneous speed of 85.8 kilometers per hour. The car is probably not going that fast the whole time. It's just at that one moment. In a couple milliseconds, that number will probably change. Okay, so it's kind of a theoretical quantity actually, because it's not exactly easy to figure out exactly how fast something is going at a very specific instant. But we can get pretty close with our approximations. All right, the example down below. Describe a world-class sprinter's instantaneous speed and average speed over the course of a 100-meter race. So, world-class sprinters, think Usain Bolt, Andre DeGrasse, those kinds of people that make the Olympics, they're going to finish a 100-meter race in most likely less than 10 seconds. Slightly less than 10 seconds. So what would that allow us to do? Well, that would allow us to calculate an average speed because then we know the total distance of 100 meters and we know the total time. But what happens in terms of instantaneous speed? So the instantaneous speed actually starts at 0. When they're on the start line, they're not moving. In fact, if they move right before the gun goes off, they may be called for a false start. So they're not moving. Their instantaneous speed is 0 meters per second. When the gun goes off, they start accelerating. So they try to build up their speed. They don't instantly go from a standstill to their top speed. It does take them at least a few strides before they can get up to top speed. So I'm going to say that it gradually increases for the first few seconds. Okay, so for the first few seconds, they go from 0 to whatever the top speed ends up being. But once they hit their top speed, after a few seconds, then they're going to try to just hold on to that top speed as long as they can, maybe even to the end of the race. Okay, so then it remains constant at top speed. And we'll just say for the rest of the race. Like maybe they'll get tired and slow down, but we'll just pretend that they don't for this example. Okay, so the instantaneous speed is changing. Starts at 0, gets higher, gets to some maximum, and then it stays there. The instantaneous speed is changing throughout time. But the average speed it's just an average. So it's just one number that we're going to calculate. And we're going to calculate it just with the formula of distance divided by time. So that would be 100 meters divided by, let's say 9.9 seconds, like a world-class time. And I'll divide that out on my calculator, getting 10.9 9.1, but we do have to, here I'll say 9.90, to three significant digits, 10.1 meters per second. So it's not as interesting. It's just a number you calculate, whereas instantaneous speed is a bit more interesting. You can think about the details of what happens throughout the entire race. Okay, the next term is acceleration. Acceleration is a change in velocity. Acceleration is a change in velocity. So we can talk about an average acceleration, which has a formula shown in purple there. The average velocity is the change in, the average acceleration is a change of velocity divided by an elapsed time. So a change of velocity is actually represented as v2 minus v1. That means the ending velocity subtract the starting velocity. That gives you the change of velocity. And we divide it by how long it takes to change that velocity. So acceleration can be manifested in three different ways, either speeding up, slowing down, or changing direction. All three of these represents a change of velocity. So you can actually stay at the same speed and be considered accelerating as long as you're changing direction, okay? Because the change of direction does count as a change of velocity. Acceleration is a vector quantity, so it needs a direction. The symbol is A with the harpoon above it, and the subscript of AV represents average. Now, possible units, you may probably have heard of meters per second squared. That is the standard one. That's the most common one. Other ones could include kilometers per hour per second or meters per minute per second. In general, it's velocity units per time units. Okay, because the formula is velocities divided by time. So whatever unit for velocity per a unit of time, that will give you an acceleration unit. So if the velocity units you use are meters per second and the time units you use are seconds, you end up with meters per second, and that's often just shortened down to meters per second squared. Okay, but kilometers per hour per second would be another example, because kilometers per hour is a velocity unit, let's say of a car. Per second, the seconds would be the time units in that case. All right, so we do have a car example down here. A car increases its velocity from 50 kilometers per hour east to 80 kilometers per hour east over a time of 2.5 seconds. Determine its average acceleration. So I'm just going directly from the formula given to me above here. I'm just going to copy down the formula first. Now I will substitute the values I'm given. (80 kilometers per hour east minus 50 kilometers per hour east) divided by the elapsed time of 2.5 seconds. You do have to be careful that you put numbers in the right order. It's 80 minus 50, not 50 minus 80. Because it's a V2 minus V1. All right, so we'll calculate that. I'll do it in steps. 80 minus 50 ends up being 30. And I have to divide that by 2.5. Let's see, can I do that with mental math? I think so. I think that would be 12. Okay, in terms of significant figures, I need 2 of them, so 12 is just perfect. Now, what about the units? Well, we're just going to copy the units from the question. So in this case, it's kilometers per hour per second. And what about the direction? Well, we're going to copy the direction from the question. East. Okay, so that would be the final correct answer, as long as I did my mental math correctly. You can check me on that. Okay, so delta D is displacement. But if an object is moving, we can talk about how fast the displacement is changing, or in other words, the rate of change of displacement. And that is velocity. That's how fast the displacement is changing. But now we just talked about velocity changing. And when velocity changes, that's called acceleration. And we generally stop there in grade 12, and probably in first year university too. But if you wanted to go further, well, what if your acceleration changes? And that would actually happen quite a bit when you ride roller coasters. You're accelerating, let's say going down a hill in a roller coaster, but then let's say it twists and it turns, goes up and then back down, you do a loop-the-loop. Your acceleration is probably going to be changing. So a change of acceleration is actually called jerk. And I don't actually know the symbol for jerk, so I'm just going to write jerk. But it is a vector, so I'll put a harpoon on it. And then if the jerk changes, now we're thinking like really theoretically here. I don't even know of a real life situation that can easily describe this, but if your jerk changes, well, a change of jerk is called jounce. And like technically you can just keep going. Well, what if your jounce changes? And what if that changes? And what if that changes? So some humorous physicists decided to give some funny names here. So instead of jounce, they say, okay, you know what? Let's call it snap. And if that changes, let's call that crackle. And if that changes, let's call that pop. So I guess whoever made up these names really likes Rice Krispies. But I'm not going to be testing you on this. We, for this class, only need to get up to acceleration. This is just for interest. Okay, so then we get to some more complicated acceleration formulas, or formulas that actually combine lots of different quantities we've been talking about. There's 5 formulas here. There are 5 symbols that these formulas share: acceleration, elapsed time, displacement, and then 2 velocities, which I'll label v1 and v2, which will represent the starting velocity and ending velocity of an object. And with those 5 variables, there's lots of equations that can be made that are mathematically true, that will relate all of them. And I listed them all here. Okay, so these equations are called uniform acceleration equations. Uniform acceleration equations. And they're called that because they are only mathematically valid when the acceleration is uniform. That means there can be no jerks. No jerks. This is a smooth acceleration. Some examples of uniform acceleration include free fall. An object falls through the air, it will accelerate uniformly at 9.8 meters per second squared. Or sliding an object down a smooth ramp. You slide it down a smooth ramp, it's going to pick up speed, so it'll accelerate, and it'll stay at the same acceleration going down that ramp. If you put it on a curved ramp, then it's probably not going to be uniform acceleration, however. So we're talking about nice scenarios here. That's how I'll describe it. Nice scenarios where the acceleration is nice and constant. I'll also call it smooth. So here's one example. A car traveling at 20 meters per second hits the brakes and slows down to a stop over the course of the next 30 meters. What was the car's acceleration during this braking period? So for these uniform acceleration questions, I kind of follow the same setup, I would guess, or like strategy. I like to list out my variables and their values given in the question. And I also like to list out the variable that the question is asking me for. So make a nice list. So I see the number 20 meter per second there. So I'm going to identify what variable that represents. And there's those 5 choices in those equations. And that would represent the velocity that the object started at. So I'm going to say V1 with a harpoon is 20 meters per second. And for the direction, it doesn't really say. So I'm going to make a general direction here called F. F stands for forward. Hits the brakes and slows down to a stop. Now, when I see the word stop, I think 0 meters per second. And that would represent the ending velocity. So I would write in my list V2, harpoon, equals 0 meters per second. We don't need a direction when it's 0. Over the course of the next 30 meters. So what's measured in meters? Well, displacement is. Okay, so I'm going to list displacement. Delta D harpoon equals 30 meters. And I need a direction, so I'm going to be general and just say forward. What is the car's acceleration? So acceleration is variable A, harpoon, and that's what I'm trying to find out. So I'll often say equals a question mark for whatever it is I'm trying to find out. That's just my preference. You don't have to put a question mark. You can just leave it blank or whatever you want to do. So with that list there, I know that I am looking for one equation that relates these 4 variables. I'm looking for the one equation that relates these 4 variables. I'm going to number the equations 1, 2, 3, 4, 5. And I'm going to look for the one that has those 4. Another way to think of it is I can look for the one that does not have the time variable, because this question has nothing to do with time. So I can look for the equation that does not have time in it. Can you spot it? It actually is the 5th one, number 5. That equation has the 4 variables I want. It does not have time in it. So I'm going to start by writing that equation down, just copying it out. And now I need to solve for A. So I'm going to just use a different color here and underline the variable that I'm supposed to get out of all this when I'm done. Now, how am I going to do that? I'm going to have to do algebra. I have to apply my math skills and isolate for A in this equation. One option is to plug in the 3 numbers that I have and then isolate for A. The other option, which is the preferred option, is to actually isolate the equation first and then plug in the numbers after. With one exception, if you see a 0, which I do see, I will actually sub that in first because that will simplify the equation. That just becomes a 0. Just makes things easier. Okay, now I'm going to isolate this for A. So I'm going to keep the A on the right side, and I need to try to get every other variable and that 2 all onto the left side. So the first thing to do is to subtract V1 squared from both sides. Okay, that was my first step. That was just an easy thing I saw to do there was like a v1 squared sticking out there, I could cancel it out with subtraction. So that's what I did. Now I need to cancel out the 2 as well as displacement from the right side. And I can do both of those at the same time with division, because they're both being multiplied to my variable a. So when doing this algebra, you think of the reverse operations. And what's the reverse of multiplying? It's division. Okay, so if I divide by 2, and I also divide by displacement, I will be left with acceleration all isolated. And then the 2 and the displacement go underneath the v1 squared, because that's how you can express division. You can express it as a fraction. Okay, now my acceleration is isolated. I'm ready to substitute the values in. So I have negative 20 squared over 2 times 30. Okay, so that's substituting those values in. Now negative 20 squared makes negative 400. And 2 times 30 makes 60. It is not positive 400, okay? You may be thinking negative 20 squared should be negative 20 times negative 20, and a negative times a negative is positive. Well, yeah, negative times a negative is a positive, but that's not what this is saying. This is saying square the 20 and then put a negative sign in front. That's what it's saying. Square the 20, which is 400, and then put the negative sign in front. The negative sign transfers over. You might be thinking of this, brackets negative 20 squared. This would be positive 400. Okay, because this is saying negative 20 times negative 20. So the brackets versus not having the brackets there, it makes a big difference. So going back to the question here, let's divide this out. I will put that in the calculator. I get negative 6.6 repeated. So this needs to be rounded to 2 significant figures because of the 60. So I'm going to say negative 6.7. Okay, that's rounded to 2 significant figures. What about the units? Well, I need units of acceleration. So in this case, it's going to be meters per second squared. What about the direction? The direction needs to be the same direction that I had in my list of variables. So this is forwards. My answer is negative 6.7 meters per second squared forwards. That's my acceleration. And it makes sense that the answer is negative. I'm really happy that I got a negative answer because this car is slowing down. This car is slowing down. So I often think of that as a negative acceleration. An alternative answer, if you want, you could say positive 6.7 meters per second squared backwards. I don't think there's a real need to do that, but it might be your preference. Negative 6.7 meters per squared backwards, however, would be an incorrect answer. All right, free fall. Free fall is a special form of acceleration. Free fall refers to an object moving vertically under the influence of gravity alone. For example, an object falling and speeding up due to gravity, or an object rising and slowing down due to gravity. So gravity is a downwards force that acts on objects on Earth. So an object just in the air well, it's going to get pulled down by gravity. Objects in free fall have uniform acceleration, and the symbol g is used for this acceleration. On Earth, g equals 9.8 meters per second squared. The direction of acceleration is towards the Earth. Often we just say down. If there's air resistance, then it's not technically a free fall, and acceleration is not uniform. In high school physics, so we're mostly going to ignore the effects of air resistance. Okay, so we're gonna pretend, so air, when objects fall through air, it makes it so the acceleration is not exactly 9.8 meters per second squared, but if it's not falling for a long time and other factors, it's actually just pretty close to 9.8 meters per second squared. So we're just gonna assume it's 9.8 meters per second squared for our problems and our experiments that we do in this course. Okay, example. A ball is released from rest from a height of 8.0 meters above the ground. What will be the ball speed just before it hits the ground? Okay. So, I'm going to follow the same strategy. So I'm going to make a list first of variables and numbers. So when I glance at the question, I skim the question, I only see one number. So that might make you a little worried. Oh, do I even have enough information? But you'll see that we do. Okay, so let me show you. First of all, the number I see is 8.0 meters. That's the height that the ball is released from. So which variable will I write there? And the variables we have to choose from based on just the equations that I showed on the previous slide are starting velocity, ending velocity, displacement, acceleration, elapsed time. So which of those variables is 8.0 meters going to be used for? Well, only one of those is measured in meters, and that's displacement. So it is going to be the displacement. Delta D harpoon equals 8.0 meters. Now, what direction is this displacement? Well, the ball is falling down. The ball started high and it ended up on the ground, so the ball traveled down. And that's the direction. That one you have to be careful with. Your instincts might, if you're not careful, your instincts might tell you, oh, it's up, it's starting above the ground, so I should say up. But displacement is which way it goes, and it goes down. All right, so what else do I have then? Well, the word rest. The word rest. The ball is released from rest. To me, that says the velocity at the start, v1 harpoon, would be 0. Okay. What else? Well, here is where we apply our free fall. So in free fall, we're going to assume an acceleration on Earth of 9.8 meters per second squared. What direction is that? That is down. The acceleration due to free fall is always down. Earth pulls things down. Okay, now the question is, what will be the ball speed just before it hits the ground? So I'm going to call that the final velocity That'll be the final velocity. And notice how I say just before it hits the ground. So after it hits the ground, it might bounce a bit, or it might just get stuck on the ground, and then the speed will be 0 after it hits the ground. But like just before it hits the ground, it's actually moving pretty fast. It has built up all this speed from falling down. So I'm expecting kind of a fast number here. All right, so I would go back and look at my equation sheet and pick the equation involved, and it ends up being the same equation as the last question. Okay, so that's the equation. Do I see any zeros? Yes, I do. V1 is 0, so I'm gonna cross that term out of the equation. That simplifies things a bit. Now I'm asked to isolate for V2, which I pretty much have already. It's just got an exponent of 2 on it, so I can isolate it just by square rooting both sides. When you square root both sides of an equation, you should put plus or minus in front of one of the square roots because, for example, 2 squared is 4, but negative 2 squared is also 4. So there's often two answers to some of these quadratic type questions. So I want to account for both possible answers. One of them might end up being inadmissible. Actually, the negative one ends up being inadmissible because I just know from the physical situation that my ball will not suddenly be going up. My ball will not suddenly have a negative velocity. So this is going to be thrown out as inadmissible. Okay, so now I can substitute my values. 9.8 for the acceleration and 8 for the displacement. I will type that into the calculator. And it is giving me 12.52. This needs to be rounded to 2 significant digits due to the 9.8 as well as the 8.0. So that would round to 13. The units would be meters per second, and the direction would be down. Now, this question asked me for speed and not velocity. So, I mean, technically, I guess I can say, I'll just write that in the sentence here. The speed is a scalar, it does not have a direction. It's instantaneous speed. The magnitude is going to be the same as the instantaneous velocity. Like it's still going that fast, 13 meters per second. You just don't write the direction when you ask for the speed. Okay, and now here's an example of a complex problem. Okay, so we'll save this, I think, for the next lesson. There's already been enough today, and I want you to practice a bit before we get to the more complex ones. Okay, so we will be saving this one for later.